Swayam Prabha. Digital India. Educated India.
In today's lecture, we shall discuss four-link planar mechanisms. As we shall see, such mechanisms have versatile applications. In fact, a major portion of this course will be devoted to the study of four-link planar mechanisms. Before getting into the four-link planar mechanisms, let us recall the technical, that is kinematic definition of a mechanism. We have already defined mechanism as a closed kinematic chain with one of its links fixed. It is obvious that to get a closed chain, we need at least three links. In the next figure, we shall see a three-link closed chain with three revolute pairs. In such a three-link closed chain, it is obvious that if one of the link, say number 1, is held fixed, then there cannot be any relative movement between these three bodies. In fact, if we apply an external load, there is no relative movement between various links. In fact, this load can be supported by this assembly. Such an assembly with 0 degree of freedom is called a structure. Hence, we see that four-link planar mechanism is the simplest mechanism that we can think of. To start with, we consider a four-link planar mechanisms with four revolute pairs. As we see, in these four-link planar mechanisms, there are four revolute pairs. One at O2, one at O4, one at A, and the other at B. The four links are numbered 1 as the fixed link and 2, 3, 4 as the moving links. These two hinges at O2 and O4, which is connected to the fixed link, are called fixed pivots, and the revolute pairs at A and B are referred to as moving hinges. Link number 2 and link number 4, which are connected to the fixed link, are normally used as the input and output link. And link number 3, which connects links 2 and 4, is called the coupler, which is the motion transfer link between 2 and 4. Such a 4R mechanism has four kinematic dimensions, namely O2, O4, which we represent by say L1, O2A, which we represent by L2. Similarly, AB is equal to L3 and O4B as L4. If one of the input links which is connected to the fixed link makes complete rotation, as is normally the case when the mechanism is driven by say an electric motor, then that link is referred to as a crank. And the output link, say link number 4, which is the output link, is called follower. And the intermediate connecting link is called the coupler. Let us now consider a 4R planar mechanism where one of these kinematic pairs, say at B, goes to infinity along a vertical direction. consequently that kinematic pair is converted to a prismatic pair, and what we get is a 3 revolute 1 prismatic pair referred to as a 3R1P mechanism. So we get a 3R1P mechanism where there are 3 revolute pairs at O2, A and B, and the kinematic pair between link 4 and link 1 is a prismatic pair. Such a mechanism has 3 kinematic dimensions, namely O2A, which is called the crank length, say represented by L2, AB, which is called the connecting rod, whose length is represented by say L3, and the line of reciprocation of B is at a distance from O2, and this perpendicular distance which is called the offset. So the other kinematic dimension is the offset, which is equal to E. This is also known as the offset slider crank mechanism, which is used to convert uniform rotation of link 2 into rectilinear to and fro oscillation of the slider 4. Now let us consider different kinematic inversions which can arise out of such a 3R1P chain as shown in this figure. Here, as we see, there are 3 revolute pairs, namely at O2, O4 and say at A. Compared to the previous 3R1P chain, here the link 1, which is fixed, has revolute pairs at both ends, that is at O2 and O4. Whereas in the previous mechanism, the fixed link had a revolute pair at one end and a prismatic pair at the other end. Here again we have 3 kinematic dimensions, namely O2, O4, that is the fixed link length, O2A, that may be the crank length, and the distance of this line of reciprocation from these fixed hinges. Such a mechanism with this offset E equal to 0 is used in a quick return mechanism that is used in a shaper. We consider again yet another kinematic inversion of the same 3R1P chain. Here we have 3 revolute pairs, namely at O2 and A and O4. Here again the fixed link has revolute pairs at both ends, namely O2 and O4. Such a mechanism is called an oscillating cylinder mechanism, which is used, for example, in a bicycle foot pump. The thing to note is that here the input member is link number 3, which is given an oscillatory motion, and this piston, link 3, moves within this oscillating cylinder, which has the same angular velocity as link number 3. We see another kinematic inversion from the same 3R1P chain, where we have a kinematic pair at O2 and at A and at B. The link number 4, which has a revolute pair at B, has a prismatic pair in the vertical direction with respect to the fixed link 1. Such a mechanism, as we know, is used in a hand pump mechanism, and here again it is link number 3 which is given the input motion such that the piston, which is link number 4, moves vertically up and down within this fixed link. So far we have considered 3R1P chain. Let us now have another revolute pair converted into a prismatic pair, and consequently we get what we call a 2R2P chain. However, unlike in a 3R1P chain, there can be 2 varieties, that is the sequential order of these kinematic pairs. For example, we can have R, R, P, P or R, P, R, P. Here the 2 revolute pairs are connected by one link. Then another link has a revolute pair at one end and a prismatic pair at the other end. Another link has prismatic pair at both ends, and this link has a P pair at one end and a revolute pair at the other. So this is what we call RRPP chain, whereas here these kinematic pairs appear alternately as RP, RP. So you see all the 4 links has a revolute pair at one end and a prismatic pair at the other end. That is same for all these 4 links. It may be emphasized that in a 3 or 1p chain, whichever way you go, we start from one prismatic pair, then it is followed by 3 sequential R pairs. So P, R, 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 that is the only possibility. Let me now consider some inversions from these 2R 2p chains. Here we consider a 4-link planar mechanisms with a revolute pair at O2, another revolute pair at O, which is I call O4, that is link number 2 has 2 revolute pairs at its either ends, and link number 3 has a revolute pair at O and a prismatic pair with 4 along the vertical direction. Similarly, link number 1 has a revolute pair with 2 and a prismatic pair with 4 in the horizontal direction. We consider a special case when these 2 prismatic pairs has an angle of 90 degree between them. From such a 2R 2p, that is RRPP chain, we can have different mechanisms by the process of kinematic inversion. For example, let us hold this link number 1 fixed. So we can see that link 4, the output link, can have horizontal movement with respect to the fixed link, as link 2 undergoes rotary motion with respect to link 1, that is the fixed link. This is the kinematic sketch. Let me see the physical construction of such a mechanism, which is known as a Scotch-Yoke mechanism. As you shall see, such a mechanism will convert uniform rotary motion of link 2 into simple harmonic translatory motion in the horizontal direction for link 4. So again we have this R, R, P, P chain. There is one revolute pair at O2, one revolute pair at A, there is a vertical prismatic pair between 3 and 4 and a horizontal prismatic pair between 4 and 1. Here, if we consider the kinematic dimension O2A as say L2, and this angle if I call theta, assuming at t equal to 0, theta is 0, then I can represent theta is equal to omega 2 into t, where omega 2 is the constant angular speed of link number 2. Then the position of this link 4, which can be represented by this point, is given by x. It is easy to see that x is nothing but L2 cosine theta, that is L2 cosine omega t. So we have produced simple harmonic motion out of continuous rotation. It may be emphasized that continuous uniform rotary motion would have been translated into to and fro rectilinear oscillation by a slider crank mechanism that we have seen earlier. However, the to and fro oscillation of the piston of the slider in a slider crank mechanism is periodic but not purely harmonic. This periodic motion tends to be harmonic as the ratio of the connecting rod length to the crank radius keeps on increasing. In fact, if the connecting rod length in a slider crank mechanism tends to infinity, then the slider motion becomes purely harmonic. As soon as the connecting rod length becomes infinity, one of the kinematic pair, which was a revolute pair for a connecting rod, gets converted into this prismatic pair, because we have already seen a prismatic pair is nothing but a revolute pair at infinity. I will now show this through a model. This is the model of that Scotch-Yoke mechanism. This is link number 2, that is the crank, which has a revolute pair with the fixed link at this point. Another revolute pair between link 2, that is the crank, and this block is here. This block, link number 3, has a prismatic pair in the vertical direction with link number 4. and link number 4 has a horizontal prismatic pair with link number 1. Now if we rotate link number 2 at a constant angular speed, as we see, the red link, that is link number 4, is performing simple harmonic oscillation in the horizontal direction. Let us now consider another kinematic inversion of the same RRPP chain. As shown in this mechanism, the link which has revolute pair at its both ends, that is at O2 and O4, is held fixed. Now link 3 has a prismatic pair in the horizontal direction with link 2 and a prismatic pair in the vertical direction with link 4. So thus, if we rotate link number 2, that is in translation with link number 3, which is again in translation with link number 4. Thus link 2 and link 4 has only relative translatory motion. In other words, they have the same angular motion. Thus this mechanism, known as Oldham's coupling, can be used to connect two parallel shafts, one at O2 and the other at O4, and transmitting uniform angular velocity ratio. This is the kinematic diagram. The physical construction of this Oldham coupling is shown in the next slide. As we see, there is a revolute pair between link 1 and link 2. Then there is a prismatic pair between link 2 and link 3, and another prismatic pair between link 3 and link 4, and the direction of these two prismatic pairs are at right angles to each other. Link 4 again has a revolute pair with the fixed link 1. Thus link 4, that is this shaft, and link 2, that is the another shaft, which are parallel, can be connected by such a coupling, and it will transmit uniform angular velocity ratio. I will now show this through a model. This is the model of Oldham's coupling. As we see, the rotation of this shaft is converted into the rotation of this shaft at the same speed through this intermediate member, which has a prismatic pair here and a prismatic pair at the top. So there are two prismatic pair at 90 degrees to each other. This intermediate member moves in and out in this prismatic pair and also at this prismatic pair. Of course, this coupling is good enough to transmit power only when the offset between these two shafts is not very large, because lot of power is wasted in friction at these two prismatic pairs. Now let us consider another kinematic inversion from the same RRPP chain. In this mechanism, we consider the link which has prismatic pair at both ends fixed. For example, this link 1 has a prismatic pair with link 4 and a prismatic pair with link 2 at right angles to each other. This mechanism is known as elliptic trammel. It will be obvious now why this name elliptic trammel. Let us consider the physical construction of this mechanism rather than this kinematic representation. As we see, this link has two prismatic pair, one in the horizontal direction and the other in the vertical direction. This rod A, B, C, D, which has revolute pair with this block at C and another revolute pair with this block at A. Now as this rod moves, let us look at the coordinates of any point D on this moving rod. This is, let's say, x-axis, this is the y-axis. So the x coordinate of this point D, when the rod is making an angle theta with the vertical, is easily seen to be AD sin theta. Similarly, the y coordinate of this moving point D is CD, and this angle is theta, so it is CD cosine theta. So YD is CD cosine theta. If we eliminate theta from these two coordinates, we can easily see that xd by ad squared plus yd by cd squared is equal to 1. That is, as theta changes, this point D moves on an ellipse with semi-major axis given by AD and CD. That is why it is called an elliptic trammel. It must be pointed out that there are 3 points on this rod AB which are exceptions, namely this point A, which generates a vertical straight line because of this prismatic pair. Similarly, this point C, which generates a horizontal straight line because of this horizontal prismatic pair, and for the midpoint B, which is the midpoint of the distance AC, that is AB is equal to BC, then if AB and BC are equal, then the point B generates a circle of radius. If I call this point O2, then the radius of that is O2B. We can say that these are nothing but the degenerated faces of the same ellipse. Now we will show you a model to generate this ellipse through an elliptic trammel. This is the model of the elliptic trammel. As we see, there are 2 perpendicular slots in this fixed link, and this is that rod AB which has revolute pair with this block here and with this block here, and these 2 blocks move along these 2 prismatic pairs. Now if we move this rod, as we can see, this particular point of this rod generates the ellipse which has been drawn with the green line. Now if we consider the midpoint of these 2 revolute pairs, then as we see, as this rod moves, this particular midpoint generates this red circle as mentioned earlier. Now that we have discussed different inversions from a RRPP chain, let us go back to another 2R2P chain, namely RP-RP chain. We consider here only the portion covered by these dashed lines. This is the part of an automobile steering gear known as Davis steering gear. Here, as we see, there is a revolute pair between link 4 and link 1. Then there is a prismatic pair between link 4 and link 3. Then there is a revolute pair between link 3 and link 2. And then there is a prismatic pair between link 1 and link 2. These are the 2 wheels of the automobile. By moving the steering wheel, we move this link 2 in this prismatic pair between 1 and 2. Consequently, these 2 wheels will rotate. So here is an RP-RP chain. Now that we have discussed 4-link planar mechanisms with 2 revolute and 2 prismatic pairs, let me now increase one more prismatic pair instead of a revolute pair. That is, can we talk of 3P1R chain? As we see, there is a P pair, there is a P pair, there is a link 1 connecting these 2 prismatic pairs. Similarly, link 2 connects these 2 prismatic pairs, and link 3 connects a prismatic pair and a revolute pair, and link 4 connects a revolute pair and a prismatic pair. It will be easy to show that we cannot have a mechanism with such 3P1R chain. For example, we can see, because there is a prismatic pair between link 1 and 2, there cannot be any relative rotation. Same goes between link 2 and 3, because they are connected between a prismatic pair. There cannot be any relative rotation between link 2 and link 3. There is a prismatic pair between link 1 and link 4, so there cannot be any relative rotation between link 1 and link 4. Thus, If we follow these three prismatic pairs, we conclude there cannot be any relative rotation between link 4 and link 3. Thus, this revolute pair, which allows only relative rotation between link 3 and link 4, cannot permit any relative motion. Thus, we can conclude that such a 3p1r chain cannot give rise to any mechanism. Now, can we have a mechanism with 4 prismatic pairs, a 4-link planar mechanism with all pairs prismatic? We will see later that such a 4p mechanism is not a constant mechanism. In fact, 3 links connected by 3 prismatic pairs having their relative translation at various angles itself constitutes a planar mechanism which is constant, but that we shall see later. So far we have discussed mechanisms only with revolute and prismatic pairs. Let me now change the topic a little bit. Can we consider mechanisms involving higher pairs as well? As we shall show now that a mechanism with a higher pair can be replaced equivalently by a mechanism having only lower pairs, that is revolute pair and prismatic pairs. Of course, this equivalence is only instantaneous and holds good for velocity and acceleration analysis at a particular configuration. So we are talking of an equivalent lower pair linkage for a higher pair mechanism. How a higher pair can be replaced equivalently by lower pairs. As an example, let us look at this higher pair mechanism, which consists of 3 links, namely 1, the fixed link, and 2 and 3. There is a revolute pair between link number 1 and 2 at O2 and a revolute pair between link 1 and 3 at O3. But there is a higher pair at the point C between link number 2 and link number 3. Our objective is to replace this higher pair mechanism by a kinematically equivalent lower pair linkage consisting only of lower pairs. I repeat again that this equivalence is only instantaneous. That means true only for this particular configuration. Towards this end, let us consider that the center of curvature of body 3 at the point C is at B. Similarly, the center of curvature of the body 2 at this contact point C is at A. Due to the property of center of curvature, that is circle of curvature or osculating circle, we can consider that for 3 infinitesimally separated time instants, these points A and B do not change. Thus, we can replace this higher pair by having a lower pair at the point A, which is a revolute pair, and a lower pair at the point B, which is again a revolute pair. And because the distance between A and B are not changing for 3 infinitesimally separated time intervals, I can join these 2 points A and B by a rigid additional link. Thus, this higher pair mechanism has been replaced by a 4R linkage which has all 4 revolute pairs at O2, O3, A and B. As I said earlier, because as these two bodies 2 and 3 move, the center of curvatures also move. So for every instant we have to have a different equivalent lower pair linkage. Later on we will explain this equivalence through a model. But we should see that a higher pair at C has been replaced by an additional link, that is link number 4, and 2 additional lower pairs, one at A and the other at B, where A and B are respectively the centers of curvature of the contacting surfaces between 2 and 3 at the contact point C. Of course, this equivalence can be permanent if the center of curvatures do not change. That is, one of these contacting surfaces, say, is a circular or cylindrical of constant radius of curvature, or flat, that is again of infinite radius of curvature. For example, let us look at this higher pair mechanism, which is a cam with a flat face follower. The cam, that is this rigid link 2, has a revolute pair with the fixed link at O2, and this follower 3 has a prismatic pair with fixed link number 1, and there is a higher pair at this contact point. So the rotary motion of this cam 2 is converted into rectilinear motion of this follower 3. Let the center of curvature of the cam surface at this contact point is at C2. The center of curvature of the follower surface at the contact point is at infinity. That is, the revolute pair at that center of curvature is converted to an equivalent prismatic pair in the horizontal direction. If we recall that a prismatic pair is nothing but a revolute pair at infinity. Consequently, this cam follower mechanism with a flat face follower is replaced by this equivalent lower pair linkage. This link 2 represents the cam, link 3 represents the follower, and there is an additional link 4 which has a revolute pair with link 2 at C2 and a prismatic pair with link 3 in the horizontal direction. This is the equivalent lower pair linkage of this cam follower mechanism. That means the input-output characteristics of this cam follower mechanism can be carried on by analyzing this lower pair linkage. Because C2 keeps on changing if the cam surface is not circular, that's why for every instant we have to have a separate equivalent lower pair linkage, because this link length C2 will keep on changing. Again, this equivalence is valid only up to acceleration analysis, velocity and acceleration, because the center of curvature or osculating circle is in contact with the surface only for 3 infinitesimally separated positions. Higher order derivatives do not match, and consequently higher order time derivatives cannot be calculated. Now I will show these two equivalents lower pair linkage by models. Let us consider this model where we have a higher pair mechanism, and this link 2 and link 3 is having a higher pair at this point. The center of curvature for this body 2 at this point of contact is here at C2. Similarly, the center of curvature of this surface of body 3 is at this point C3. Now, as we said earlier, we can have an equivalent lower pair linkage by having a revolute pair at C2 and another at C3 and connected by an additional rigid link. So thus we have a 4R mechanism which is instantaneously equivalent to the original higher pair mechanism. I have connected these two bodies, that is this red link and the original link number 2, rigidly. And as we shall see that where I can move this mechanism, the same motion is transmitted at least around this contact region between body 2 and body 3, whether it is through the higher pair mechanism or through this equivalent lower pair linkage. To distinguish the movement of this body 3 in the lower pair linkage and this body 3 in the higher pair mechanism, let us notice at these two lines there is a red line on this body and there is a blue line on this body. Now, around this point, as we see, these two lines move almost the same way, because the velocity and acceleration relationship between the original higher pair mechanism and the equivalent lower pair linkage is just the same. But however, when there is a lot of movement, these two lines separate out. This blue line and this red line are not same anymore. But around this point, it is only here
that these two lines separate out, because the centers of curvature is very different from what it was at this configuration. So this is what we mean by instantaneously equivalent lower pair linkage. We can show another model with one surface flat, that is the radius of curvature is infinity, and the other curvature is a circle, that is radius of curvature is constant. Under such a situation, of course, the equivalence will hold good for the entire cycle of motion. A higher pair mechanism between link number 1, 2 and 3, and the center of curvature of body 2 at the contact point is here, whereas body 3 has a flat or straight contacting surface. Consequently, the extra link that is having here gets a prismatic pair between body 3 and that extra link, and a revolute pair between body 2 and that extra link. If we connect these lower pair linkage, link number 2, with the link number 2 of the original higher pair mechanism rigidly, then we can see that same motion is transmitted by both the lower pair linkage and the higher pair mechanism.
So let me now summarize what we have talked so far in this lecture. What we have seen that 4 are planar mechanisms of different varieties consisting of 4 revolute pairs, or 3 revolute and 1 prismatic pair, or 2 revolute and 2 prismatic pairs. When we have 2 revolute and 2 prismatic pairs, the order or the sequence of the pairs become important. We have talked of 2 varieties, namely RRPP or RPRP. At the end, we have also seen that we have a 3-link mechanism with a higher pair, then that also can be equivalently represented by a 4-link planar linkages having only R pairs or R and P pairs.